Joy, shall we start?
Yeah, Professor Murthy, thank you.
Welcome, sir.
Professor Murthy, can you hear me?
Yeah.
I said very much.
Yeah. Okay. Thank you so much. Yes. So shall we start? Yeah. So Ravi Kiran, please go ahead. Thank you, Ravi Kiran, for organizing these events. Thanks all the students and also my colleagues for actively participating in organizing the event, actually reaching out to the sponsors. I must say the Physics Society of IISER-TVM has been doing a wonderful job, starting from organizing outreach programs, quizzes, talks by eminent personalities from all areas of physics and so on. So very well done. And with that introduction, I invite our director, Professor J.N. Murthy, to say a few words and inaugurate the celebrations.
Thank you. Thank you, Professor Joy Mitra and the secretary or whatever that you probably have termed or named the person who introduced Ravi. Is that right? Am I right?
Yes, Ravi Kiran.
Ravi Kiran. Okay. Yeah, at the outset, I think I must thank all of you for thinking about me on this occasion. It's a wonderful thing. I think, as both of you talked about, the Psi-T, I thought maybe some kind of a symbol that we are all used to, but then very lately I connected while looking at the slide here. Okay, it refers to Physics Society, PSIT, standing for Thiruvananthapuram. That's wonderful, wonderful. I think there is some kind of a creativity that I see, be it with our logo and coming up with Psi-T, referring to Physics Society of IISER-Thiruvananthapuram. We have something like this in Chemical Society. Chemistry being my subject, I can talk a lot about it. In fact, I sort of provocated a few that the department should have a society for itself, where it's not just run by some faculty or the students or the staff members, and everybody that belongs to the family of chemistry is part of. And which is what I was basically asking, Professor Jai Mitra. Is it something like Chemical Society that you have in the name of Psi-T? But then he said, no, it is completely student hosted, student run, student managed, and we are only occasionally participants, and some faculty become part of it and some faculty are not part of it. I think if that is the case, I think I must basically congratulate and I really applaud the student community to have taken up taken it up upon themselves and gotten started. Then that brings up a question. What then are the faculty doing? Why is it that everything has been Vinayak Kamli? I think you've not been active enough, looks like. Right? The faculty should be in the forefront. And it's unfortunate that we have not had something called as a physics society of IISER-TVM, wherein everybody is part of. I think this is the suggestion that I have for all of you. It has been started by the students. Of course, some faculty have been guiding them. Why not expand this into a larger ambit to include the faculty, the staff members, and the technical staff associated with the department, and pretty much everybody. The way that we do it, just not here. In fact, most chemistry departments have these chemical societies. The way that we do is that the members, particularly the earning members, PhD students and faculty, contribute a nominal amount. And in a department like yours and chemistry, where we keep buying a lot of stuff from time to time, right? The suppliers are invariably there to sort of contribute in a tiny amount. All that adds up. And we do it typically, conduct 3 events. One is when we get started with a new batch, the new members that become part of the family, invite them, what we call as a freshers welcome. And then in the month of October, we have the Nobel Prize basically declared. And depending on the topic, organize a talk to the benefit of the entire community, not necessarily physics, but then the whole event is sort of conducted by the whatever society or the society members. In fact, a faculty member is invariably chosen for every year as the chairman of the society, of the physics society here. And who will oversee or guide the students in terms of conducting the programs respectively. And towards the end of the year, the minimum 3 programs. For the batch that is leaving, organize a farewell party, right? And during which time the batch that has spent a considerable number of years in the campus can reflect on where they possibly went wrong and what possibly could be a good thing for their juniors to sort of embrace and set things right that are not in order. Right? All this kind of a gossiping and talk can happen during the farewell. And that's how the integration happens. The students that join to begin with sort of recognize their seniors who are part of the members that are part of the department, get to know the faculty because everybody comes under one umbrella. And the fabric, the interaction amongst the members of the same family gets stronger and stronger, and everybody would know who to approach. I think this is a very good thing, and also allows once in a while to get out of this monotony that every one of us suffer from, right? And life has to be enjoyable, and you should really love doing what you're doing. From that point of view, organizing something like this from time to time, keeping abreast of the developments by inviting practitioners to talk to you. I think I've been told this year's Shanti Swarup Bhatnagar Prize winners are going to give talks. That's a wonderful thing. I think they have been recognized for some contributions. It would be really wonderful, very nice to sort of listen to these winners as to what kind of work has really fetched them this kind of, the coveted prize in the country. It's a wonderful thing. That way the students also would know what is really latest and what are the contributions for which the country has recognized a few individuals, right? And exposure, which is when the students begin to learn. I think the way to see this is I can only say this is a fabulous thing, fantastic thing that the students have gotten started with. This is the second in the series. I think you should continue this every year and increase the number of activities, facilitate interaction amongst the students, and in the process, if the faculty are not willing to be part of, drag them into it, trust on them, and make it expand this, guys. Expand this to include everybody that is part of the department and make it a grand success every time. I don't think that I have to say more than that, and I wish the week-long activities a great success. Thank you very much.
Thank you, Professor Murthy, for your words. Ravikiran, I think you can take over. We have Dr. Kanak Saha, who has joined us for the talk. So please take over.
Thank you, Ravi. Now, welcome everyone. Knowing a little about the speaker, Dr. Kanak Saha is an associate professor at the Inter-University Center for Astronomy and Astrophysics, Pune. He was awarded the Shanti Swarup Bhatnagar Prize in 2021 for his breakthrough discovery of a faint galaxy at high redshift using AstroSat, which is India's first space observatory. He received his doctorate in astrophysics in 2008 from the Indian Institute of Science. He has held multiple postdoctoral positions at the Raman Research Institute, Geneva Observatory, the Max Planck Institute for Extraterrestrial Physics, and more. His work focuses on the formation of galaxies in the early universe and their subsequent evolution. He studies the high redshift universe using UV telescopes on observatories including AstroSat and the Hubble Space Telescope. He also uses cluster computer simulations to study the dynamics of galaxies. With that, I'd like to invite Dr. Kanak Saha to give his talk. On to you, sir.
Thank you very much. And I really appreciate the activity the Physics Society is having in the Institute. I would love to hear more. And thanks a lot for having me. So with that, I'd like to start my today's presentation, and I would try to keep it at a simpler level so that it's more for the students. And and then let's see, we can initiate some discussion and what AstroSat is doing, because this is our own made in the our own telescope in many sense, and the discoveries and the work that we are doing is exactly it's a lot of credit to our own scientific community in the India. And so let me start. Would like to share my screen.
Yeah, Dr. Shah, if you could kindly share your screen.
Yes, present now is the one.
Yes, yes, that up arrow.
Okay, entire screen.
Yeah, that would be good if you share your entire screen.
Can you see this screen?
Yes.
Okay.
Absolutely. Please go ahead.
Yes. Thank you very much. And so I would today going to talk about this extreme UV photons, the detection of extreme UV photons from AstroSat UV deep field. So as I said, that this work would not be at this state, even the detection of the extreme UV photons without the AstroSat UV deep field. And this is I think, as far as we understand, this is the first time we detect extreme UV photons from a distant galaxy. Okay, and that is to using AstroSat. So I'll try to motivate you or build a bit of an introduction to understand the various technical terms, and then I will go into the slightly more technical stuff, which is related to the detection and how we model this object. And at the end, there is an important quantity nowadays is coming, that what fraction of these extreme UV photons actually leave the galaxy. And that is one of the main topic that I will be discussing. This is a very simple stuff, as you know. This is mainly for towards the students, and apology for the senior researchers and faculties who, for them, it will be very trivial stuff. So as you know, like now we receive light from the stars, and for example, here we show the light from the sun, and it kind of follows very well the black body radiation, okay, which is described by the Planck's law. And the Planck's law is very unique when you specify a temperature. As you go to the higher and higher temperature, the peak of the black body radiation shifts towards the shorter wavelength side, right? And then as the temperature goes up, like for example, if it is like say 80,000 Kelvin, you can put in your numbers here, you will get a lambda peak, which is around 362 angstrom. So that's the extreme UV radiation or extreme UV photons. In our context, in a broader context, we call extreme UV photons are all the photons that have wavelength below 912 angstrom, or the energy greater than 13.6 electron volt. For obvious reasons, you may have guessed that this is the energy required to ionize a neutral hydrogen atom into proton and an electron. So this radiation is so all the photons that have higher energy would be able to do that, and that has a special significance, and which is why we are talking today. The stellar spectrum, you could see this is one of the stellar spectrum for A-type star. You can see as you go from on the upper right, I show the synthetic stellar spectrum for M, K, G, which is just a sun-like star, and you go to the more brighter and massive stars, the A, B, and O type star. For them, the spectrum shifts towards the bluer side or to the shorter wavelength side. This type. Now, this is a very elementary for the HR diagram, but I would say that on the y-axis we plot the luminosity of the star. On the x-axis you see the temperature, and temperature increases as you go towards the left side. And you can see that on the Huxley-Russell diagram, the massive stars have very high temperature, the surface temperature. Now the star that live on the main sequence, their lifetime is inversely proportional to the mass to the power 2.5, wherever it comes from a simple calculation. And more massive the stars, the shorter they live. So in other words, the hotter they are, the brighter they shine, and shorter they live. So that's a message to keep it in mind, because we will be using this in a later phase. Now, when you look at the light from galaxies, or in fact, when you go beyond the Milky Way, it is the light from galaxies which we receive. Okay, and galaxy consists of billions of stars. For example, in the Milky Way, you will have around 10 billion stars. And this is a bit of a digression, but I think it is useful for our context here. On the left side, you see this is a diagram of the Milky Way produced by a famous astronomer, William Herschel, in 1785. This was a sun-centric Milky Way diagram. You see now the present context, this is also an artistic impression of the Milky Way, but Milky Way is no longer sun-centric. We have a black hole at the center, and there is an elongated structure which rotates at its own pattern speed, and the sun goes around the center of the Milky Way with a speed of around 220 kilometers per second. So except Milky Way, so where we can look at individual star, but outside the Milky Way, for all other galaxies, we receive mostly the integrated light along the line of sight. So our information is actually limited as we go to outside the Milky Way. Now we can also receive light, but in different wavelength, because that is what astronomers do. They basically study objects in different the wavelength regime. And as you know that the visible is like a very tiny window available to us. Apart from the visible window, things are really require very different kind of facilities. On the ground, of course, you can have on the higher wavelength side radio and sub-millimeter and millimeter wavelength. But if you go to the shorter wavelength side, for example, UV, which is blocked by the upper atmosphere. So to study the UV light from a galaxy, one has to go to the satellite, the space-based detectors and the telescopes. And the different wavelengths carries different physics and different information. If you look at on the same galaxy has been looked at into different wavelength. On the infrared, you see on this red color stuff. On the middle, you have optical, and then you go here on the left side, there is UV. Okay, and you can see that when you look at in UV, they don't look like at all the galaxy. So in fact, the UV or the far ultraviolet radiation from a galaxy is really tell very different things than what we know about an optical picture of a galaxy. Okay, as we know that this way it helps connecting the previous slide where we talked about the more massive the stars, the peak shifts towards the UV and they would emit the light. So in other words, if you receive UV or far ultraviolet light from a galaxy, in most cases they would refer to very young star forming events. Okay, and generally they are short-lived. In other words, we can also say from this is that if you want to know the full physics of the galaxies, okay, how they are formed, how they are forming stars, how they are assembling, and all kinds of the question that comes to our mind, you need many sampling in many different wavelength, or in other words, multi-wavelength picture or multi-wavelength facility is very much in requirement. But this becomes progressively difficult as you go to distant and more distant galaxies, like the far away galaxies, because because of the reason that the light which is emitted from an object will be redshifted. It is moving away from us, right? And with a factor which is 1 plus z, which is the redshift of the object which is emitting. So we measure this redshift by measuring the shift in some strong emission lines or strong lines rather, spectral lines. You can see one can use, for example, hydrogen alpha line, oxygen 3, many different kinds of strong lines can be used, and we look at the shift, and that's how we can estimate how far away the galaxy. And this is the most accurate method to measure the redshift of a galaxy. But often the spectroscopic observations are very costly in terms of a time that it needs. Okay, so people try to look at into many other different ways of measuring the redshift. One of them is probably, let's say, a band dropout technique, I'd say. This is particularly useful for high redshift galaxies. Here you can show that there are some pass bands, and where you can observe light from a galaxy. And it may happen that depending on how far the galaxy is, that maybe light maybe in the shorter wavelength window is missing, and suddenly it appears in another the higher wavelengths, this thing. And then that's where it just starts missing, that can be used to measure the redshift or the distance of the galaxy. This has been used and there is some more, but just to give you basically glimpse of what astronomers do. These are the pictures or the images taken by Hubble Space Telescope, except the Milky Way one. This is artistic impression. What I show here is how the high redshift galaxies look like when you look at them. So as you go to the higher and higher redshift, let's say 0.5, 0.92, 1.6, 2.3, and redshift 7, 10, and one of the highest redshift galaxy 11.1, which is observed in infrared. It's all shifted towards the infrared. Now, if you look at the particular epoch about the redshift 1, 2.3, you can see they are very different from what the local galaxy look like. Now, our low redshift galaxies, what they look like. In fact, the high redshift galaxies look like more clumps here, like there are blobs kind of, right? So they must be like sort of very younger stage of assembling together to come to this phase in the low redshift universe. Okay. Now, as I said, that as you go to higher redshift, since the shorter wavelength sites are not available to us, so it becomes really difficult to do a multi-wavelength analysis. At the same time, we miss all the information that would be otherwise available from the shorter wavelength site. Here I show an analogy just to understand the level of difficulty that we face in astronomy. And you can see, if I show you a picture of a tadpole and a toad or frog, and if we did not have this idea of the life cycle of the tadpole, we would not be in a place to comment on whether the tadpole has evolved to the frog. In a similar way, we have a high redshift galaxy. It's an early universe, and this is the present day galaxy. This is how it looks like, much bigger, much more matured from here. So if the early galaxies have evolved and come to us today because of various processes, physical processes, which is needs to be decided. So you can see it's a tremendous task, because the tadpole have a life cycle which we know, so we can connect all the pieces. But for galaxy, we don't know the full life cycle of a galaxy, because we observe only one galaxy in the sky, and it's in its own pace only. So we don't know the past history, neither the present. We know only the present, what we observe. So we cannot go back and see how these galaxies were before. So this is a connecting from this high redshift to low redshift is one of the biggest challenge in astrophysics now, and this is what lot of us are trying to understand all over the world, that how to solve this problem, because before the early universe, the physics is much well understood. But when it comes from the galaxy evolution from very early universe to now, there's a lot of nonlinear physics comes into picture and events that we don't know. Okay, so it makes it really, really difficult for us to connect these. Of course, nowadays people look at the cosmological simulation, where they simulate a patch of the universe and form galaxies and try to so that's kind of complement us to understand this picture. But observational side, it's really, really difficult task. And I just wanted to show that there are actually a lot of galaxies in the high redshift. They look like indeed a tadpole with a bright head and a comet-like feature. So coming back to now is that what are those kind of galaxies? Now that we know what the different galaxies look like, what are the galaxies which would emit extreme UV radiation? So to understand this, we go back past in the early phase of the universe, and let's go through this diagram, try to understand what was happening in the early universe. So I won't go to like the very big bang, because for us what is interesting is that when the universe was around 4,000 years old, just 4,000 years old, compared to what today is 13.8 billion years old, or at a redshift which is around 1100, the universe completed the what is called the recombination era. Okay, when the protons and electrons combined and formed hydrogen atom. And when the recombination era completed, there were no stars, there's no galaxies, the only hydrogen gas everywhere. Of course, there were some helium and some amount of lithium that was produced in the Big Bang nucleosynthesis. They were there, but majority dominant component is where the neutral hydrogen gas. And since there are no stars, no galaxies, the universe went through a dark age, dark phase from about 4,000 years old to about 0.1 billion years old. Okay, and then the first stars and the galaxies formed. The first galaxies that formed in the universe, they formed, of course, from the first stars. We don't know anything about them, but we hypothesize and we try to understand them from very basic physics, that the first stars that form, they are almost like metal free. In fact, they are made from a hydrogen atom, and they would be very massive, much more massive than maybe around hundreds of solar mass star that would form. When, as you know, that in the first few slides we learned, the most massive the star, shorter the live. Okay, so those massive stars would live a very short duration of time, and before they explode into supernova explosion. So that's the kind of hypothesis that we know, that the first stars, which is called the POP3 stars, they must be very massive and short-lived. So the first galaxies were they're made up of many of these POP3 stars. They would and then there's another point which I wanted to bring, that as you know, that when the stars is very massive, the short-lived, and the most massive stars are also emit in very much in the UV. Okay, so those stars, the first galaxies, would be source of a lot of extreme UV photons. When these extreme UV photons come out of this galaxy, okay, they would try to ionize the hydrogen gas in the surrounding medium. Okay, and then that's how the universe went into a phase called the reionization phase, and that's the phase which is lasted for quite some time, up to about 1 billion years old, when the universe was just 1 billion years old. Okay, now from during this is a very important phase transitions in the galaxy. Okay, by around redshift 6, we think that the universe completely ionized, and radiation could pass through, and we could see everything that is possible through the yeah. So there is a lot of interesting research at the moment going on in the country and elsewhere. When did this reionization phase started? What was the morphology, topology of this, how the reionization occurred, where it's patchy in blobs, and all kinds of the information, or the questions that actually that comes to us. And for me, the most interesting question that I'd like to address is that what kind of sources, or what was the nature of those galaxies, the first galaxies, okay, which we cannot observe. Now, what was the nature of them? Okay, and so that's from astrophysics point of view. That's kind of my interest, and that's where we go. Now, it seems that in the low redshift universe, these extreme UV photons are really rare. Okay, means that extreme UV photons, do not come out of the galaxy. And here is a cartoon that show that, as you can, maybe you may have heard about the Storm sphere. So you can see that if you have a starburst event in some part of the galaxy, then the radiation from the star they will try to ionize the hydrogen gas. So there is a ionized gas. H2 means the ionized hydrogen, and then H1 means neutral hydrogen. So you can see that ionized hydrogen and then surrounded by a neutral hydrogen gas layer. And we can compute the mean free path of these Lyman continuum photons. We can say the Lyman continuum photons, the below 912 angstrom. We can sometimes will say ionizing photons, sometimes the extreme UV photons. So they are I will use synonymously. Okay, all wavelengths are below 912 angstrom in the rest frame. Now we can compute the mean free path of those photons considering the ionizing photons cross section. If we know the neutral hydrogen gas density, and it comes to around half a parsec, which is much less than the Storm sphere, which can be around hundreds of parsec for a O-type star if you put in. Now you can see that the photons would not escape, so they would get absorbed by the neutral hydrogen gas unless and until there is a hole somewhere of low density hydrogen gas and maybe low dust and low hydrogen gas, the column which is open and channel is open through which this ionizing photons would escape. We don't know which of these, the other picture in which the Storm sphere is incomplete, but which means that the starburst is so strong that it basically there is no neutral hydrogen gas layer. So both the starlight and everything is mixture and will come out. So that's not quite useful. But we don't know which of this picture is true at the moment. But what boils down to that this is a very challenging task for the ionizing photons to come out of the interstellar medium of the galaxy in general. We had recently published a paper in which we show evidence of a density bounded region. This can be a bit complex, but I do not want to get into there. But there's a one. So as I try to show you here, this is ionization bounded nebula and the density bounded nebula. Which is the picture right now, a favorite picture for the escape of the ionizing photons is not clear. So unless and until we have a clear picture with an observational evidence, we cannot, everything is sort of a hypothesis in some sense. So here we try to show that in the region where there is a huge starburst happening, which is called a blueberry kind of galaxy, and we show that and that's where we have evidence for escaping Lyman alpha photons, and those Lyman alpha photons are shown in such a way that the one part is bit more dusty and one part bit more less dusty. So it seems there is evidence for the whole type of the picture in this. Anyway, so what you probably get here is that the ionizing photons is difficult to get out of the ISM, the interstellar medium of the galaxy. Even if they get out of the interstellar medium of the galaxy, there is a circumgalactic medium which is surrounding the galaxy. Okay, so these photons that if somehow they escape a fraction of it to the outside the ISM, they can be absorbed in the cesium, and if somehow they manage to escape both the interstellar medium and the circumgalactic medium, there is a huge path from the galaxy to us, and which is filled with the intergalactic medium, which is having clouds, which also can absorb these ionizing photons. So at the end, what you receive is tiny fraction or almost nothing. So that's how it is the state. And I'll show you that that it's a challenging task in many different ways. And this is where the people who simulate the intergalactic medium, like imagine the galaxies emitting photons, which will pass through various clouds, and they compute the transmission probability, and the transmission probability, the red curve if you follow, is at redshift 6, is almost 0, which means from this redshift, which is marking almost the end of the reionization era, or in fact redshift will be higher. So the transmission or the photons, ionizing photons that will manage to escape from that far will be very, very low probability. Okay, and that is why, in fact, there is every 2 year a conference goes on escape of Lyman continuum photons, and this is why one could think this is a cartoon is of a labyrinth, in almost it says that it's Lyman continuum photons is basically are lost in this labyrinth. So escape is not an easy. Okay, so that's where we come into picture, and we would now get into the AstroSat UV field. And before I get into the showing how the deep field looks like, I want to bring 2 points here. Now, why study deep field? Right? What is the big thing about the deep field? So the deep field allows you to do one thing in a unique setup with in which one can look at fainter galaxy and further galaxy, like many distant and the fainter galaxy, because you can imagine brighter galaxies are all observed. So there is no point in that doing that again. What happens is that on the right side I show a plot of the luminosity function. Okay, on the higher luminosity, the curve is falling exponentially. On the low luminosity, which means the fainter galaxies, are there many more in number. So if we have a better sensitivity telescope and we have a better detector, we can actually get a handle on this number, on how faint we can go, what is the number of the faint galaxy counts actually. So this is why deep field is very useful. And then another thing is that you will see that the AstroSat deep field that we will talk about is very unique in terms of probing ionizing sources between redshift 1 and 2. Why redshift 1 and 2? This plot shows the star formation history of the universe itself, from very early universe to now. Somehow the star formation history seems to have peaked around redshift 1 and 2, which means between this epoch, redshift 1 and 2, a lot of galaxies were forming stars. Okay, and AstroSat deep field is really the filter is such that it's sensitive and it can probe this region, which other telescope couldn't with the same sensitivity. So we observed the famous Chandra Deep Field South, and Chandra Deep Field South is near the Fornax constellation, and you can see that a small patch of the sky with a knot of bright object. In other words, you try to choose an area which is not crowded by many bright stars, and observe this is for a long time. Okay, and you can integrate your observations and produce a deep images. So these were the two fields which is centered around the Booth South or the Chandra Deep Field South, and we observed this using AstroSat. Okay, and the UV telescope on board AstroSat had two co-aligned telescope. One works in near ultraviolet, one works in far ultraviolet, with an aperture of a small 37.5 centimeter. Okay, and the wavelength range in which the far ultraviolet filter works, which is around 1300 angstrom to around 1800 angstrom in the observed frame, and in near ultraviolet it works for around 2000 angstrom to around 3000 angstrom. So that's the wavelength redshift. We observe the deep field in one of the two filters, okay? One in far ultraviolet, one low ultraviolet. Using UVIT observations, one can do simultaneously observe the same patch of the sky in far ultraviolet and near ultraviolet. And when you take the frames in a normal settings, between two frames, like when you take snapshots menu, so there are 33 milliseconds around the time difference. And in a typical good dump orbit, you have a 1500 seconds of image. And so in a typical dump orbit, you will have a 45,000 such frames, short frames. Many a times, depending on the time of the observations, or this is a random event, the frames will be affected by cosmic rays. So around 10% of these frames in long observations may go into the cosmic ray showers, and these are the cosmic ray affected frames. We do not take into account the cosmic ray shower frames into our subsequent image making. So we remove them. This is how it looks in one orbit image. Okay, it's very unimpressive, and you can see only tiny dots of thing is mostly pixelated in near ultraviolet. What we do here is that we have about 40 such orbit image. Okay, each around 1400 seconds, 1500 seconds. It can be also 1000 seconds. Okay, and then from each from one orbit, we keep this as a reference. We go to the next orbit image, and we see the same objects which are marked in green here will appear at red. In another orbit, it will be appear in different position. So what we do is we keep one of the orbit, the image, as a reference, and shift and rotate the image in such a way that it aligns with this reference image, and stack them together, all the 40 orbit image, and that's how we create this. Okay. So this doesn't look like very glazing an image, but for the deep field, it's very interesting, as you see. This one looks like in how it looks like in one orbit image, like a zoom in picture. Here you can see. Okay, and this is how it looks like a bit more zoomed in, and the blue color squares are HST, Hubble Space Telescope, the UDF, which is called the ultra deep field, and this is a candles field. Okay, and this part is called the extreme deep field. Okay, Hubble extreme deep field. Now I'm going to show you a bit more detail here. So this is the image that I have created using 4 filters, 2 from the HST and 2 from AstroSat. Cyan and blue are interesting for us because that's the AstroSat. And bright objects, as I said, we don't study. We are interested in the fainter, bluer objects in that. And then we estimate the 3 sigma detection limit. Means when you look at an image, deep field image, you have to not only any image, you have to make an estimate at what faint level one can make an image that a source or the object should be reliably measured. So to that we estimate what is called the 3 sigma detection limit, which is 27.9 AV magnitude, and in HST, in the same filter, is a little bit brighter. So in other words, what I wanted to say here is that with AstroSat we could go 0.5 magnitude deeper or fainter than what HST could. So that was a big achievement for us. So this is the galaxy I'm going to talk soon. So there are many science goals with the possible with the UVIT. So various students and postdocs are working on these various science projects. So I'm going to talk about these deionization sources and the hunting of them. So before AstroSat, what was before AstroSat? This is the plot which I showed before AstroSat. Here, what you can see is that at this x-axis is the redshift. And the y-axis is the ratio of the two fluxes. One is called the FLYC, means the photons whose wavelength was below 912 angstrom, and one at 1500 angstrom. So in other words, this ratio is basically called the flux ratio of the ionizing photons to the non-ionizing photons. And you can see 2016, when we were preparing for the observations, where the observation just completed, first detection of extreme UV photons or the Lyman continuum photons came into picture. So these are not more than 5 years old. Okay, and then when, since it took a long time for me, I spent around 2 years to produce that deep field that I showed you because of various reasons. The 2018, when I almost were ready with the deep field, there was another paper came with the Lyman continuum photon detection. But anyway, we had this wavelength, this redshift range from around 0.4 to 2.5, where remain deserted. Okay, there was no detection from HST. There are large HST programs were there, but they were unable to detect this thing. Another thing you see, these are color coded each observation. Okay, and with the color coded by the rest frame wavelength. The rest frame wavelength is 850 to around 900 angstrom. Okay, that's interesting. And another interesting part is that these low redshift galaxies are the so-called, you may have heard about the green pea galaxy, the blueberry galaxy. If not, just search. It's a very interesting thing for this address for the students. So green pea galaxies are tiny compact galaxies which are emitting in oxygen 3 line, oxygen doubly ionized oxygen line, which is around 5,000, which is wavelength of 5,007 angstrom. Blueberry are also the same but at the low redshift. So these are the two kind of galaxies that are populating this field. These are also compact galaxies. These are tiny galaxies which are not even resolved sometimes with the HST. Okay, so in our case, if we know the redshift of a galaxy, we will know what is the Lyman limit. Lyman limit is determined by 1 plus z times the 912 angstrom. Okay, so if you put redshift around let's say 1.4, which I'm going to talk about, so Lyman limit is 2200 angstrom. Now our FUV filter, I told you, goes from the 1300 angstrom to 1800 angstrom. So entire filter will be within the Lyman limit. Okay, so in other words, with any source that is detected in far ultraviolet filter, and if it is at a redshift around 0.97 or higher, then that light from that will be totally within the Lyman limit. Okay, like here I show the filter response. This is the far ultraviolet filter, this is a near ultraviolet filter. At redshift 1.42, you can see that the far ultraviolet filter is within the left side of the Lyman limit. So entire detection, whatever the light that is get detected in this far ultraviolet filter, will be considered as Lyman continuum photons. These are the team members. I'm going to talk about the first detection very quickly of the Lyman continuum photons at redshift 1.42. Okay, and here I am going to go through a very slightly how we found this galaxy. That is the story here. So we searched, we took a catalog of galaxies for which there is spectroscopic redshift available. So we took about 1500 such galaxies. Okay, and then we looked for simultaneous presence of hydrogen alpha line, oxygen 3 line, which is doubly ionized oxygen, and then Balmer series line H beta. This gave us a redshift range and about 948 galaxies. And then that's how we downsize the sample, and we look for 38 objects in the Hubble extreme deep field that I showed you. Okay, and of the 38 galaxies, we have only 2 objects for which we had signal to noise greater than 3 measured in far ultraviolet, and of the 2, we had 1 object that had a very high equivalent width of hydrogen alpha line as well as oxygen 3 line. Okay, which means that these objects or these galaxies have very little continuum in that, and we chose these objects to further study. So this is the object in AstroSat filter. This is the image of the AstroSat filter. If we zoomed in like in this, it looks very noisy though. And if you zoom in and do some processing here, you see that there is a clear detection, but at a signal to noise of 3.2 only. Okay, so but this was the first time. At the same location in the near ultraviolet filter, we detect with a very high signal to noise, which is like 10. So this is a simultaneous detection between in far ultraviolet and near ultraviolet filter. And then at the same location, there are HST objects also. I'll show you. So here, the galaxy is observed in almost many other filters. So there is a lot of multi-wavelength observations from optical to infrared to like Spitzer. Okay, so this is the image of the galaxy in HST. Okay, 3-color filter. You can see that the galaxy has 4 clumps: C1, C2, C3, C4. Okay, so this is the there was a question that came to us before even we went for the publication, that whether all the clumps are at the same redshift or do they belong to the galaxy, right? What if one clump is in the foreground, right? In front of you, or say the background, so we don't know. So for that, we took advantage of the HST GRISM data, which is called the slitless spectroscopy, which show very clear emission of hydrogen alpha line and oxygen 3 line, doubly ionized oxygen. Very clear detection of the line here. So we chose to take this the hydrogen alpha line, the image, GRISM image, and each pixel from there was mapped to the direct detection image at another infrared filter. Okay, and that's how we determined the spectra from each of the clump, like C1, C2, C3, C4, and try to see that there is a detection of H alpha line. Although from C4 the detection is really low, signal to noise is less than 2, but all the lines that come at the same location and at the same redshift within the error, which is around 1.42. So we concluded that all the 4 clumps were at the same redshift. Okay. Then since we have a multi-wavelength observation from the far ultraviolet to the near infrared, okay, from the Spitzer, we did what is called the spectral energy distribution modeling. This is also like very useful for extracting various physical parameters, okay, which are standard in astronomy, and through which we measure the mass of the star, which is around 1.4 into 10 to the 9 solar mass, much smaller than Milky Way, and we get an integrated star formation history or star formation rate, which is like making 55 solar mass per year. One interesting point that you look here is that this is our far ultraviolet observation, which is at around 600 angstrom, which is with from the left side, the first data point, right? And this model could not explain that observation. That means the far ultraviolet could not observe. That could not explain. So we did some different way of modeling, like the binary stellar population modeling, and using a cloudy modeling as well. This was done by a student in Geneva who is doing PhD jointly with me, and we found that you actually need a low column density of gas to and also low dust, very much low dust, okay, to explain this observation. Okay, so that's how we could model this. Okay, and as I said, that this is the first clumpy galaxy from which we detect Lyman continuum radiation. Before that, it was only this compact galaxies like green peas and blueberries. And since this window is redshift 1 to 2, there are many other galaxies which are clumpy as well at the same redshift. Okay, so this gives us an understanding of the usefulness of AstroSat to this wavelength, to this the redshift range. Okay. Now the last technical part, I think, where I estimate that how much of this ionizing photons actually escape the galaxy. Okay, this is standard textbook stuff. Okay, this is like very good, like you can just follow. So what we do is basically we assume the photons, the ionizing photons that could not escape, means the ionizing photons that were used in the recombination event, which is a dynamical equilibrium within the storm wind sphere. And we can estimate the number of non-ionizing photons, number of ionizing photons that could not escape. And if you do a little bit of this analysis, we can, if we have the Balmer series line, hydrogen alpha, hydrogen beta, and the luminosity, we can estimate this number of photons. Okay, and as I showed you, we have a very good detection of hydrogen alpha line using the slitless spectroscopy. So we use that to estimate the number of photons that could not escape, the ionizing photons. And the number of photons that escape, that was easy, because we just take the luminosity of the far ultraviolet filter, the flux that is being detected in our far ultraviolet filter, and we estimate the rest frame number of ionizing photons that actually managed to escape. Then the escape fraction is basically, or the number of photons that escape is basically the amount that escaped and amount that produced, which is sum of the two. Sorry. So this gave us an escape fraction value of 0.2. It's very clean, which means there are at least 20% of the photons escape the galaxy. We do in various other methods also, but there's no point in going right now. So here I show the distribution of the escape fraction, which peaked around 0.2. Okay, because we have an IgM distribution as well. Okay, so we can actually do a probability of the escape fraction. But bottom line is that we have at least 20% of this Lyman continuum photons or the ionizing photons or the extreme UV photons that escape the galaxy. Okay, so we have, after the AstroSat, we have one data point right here. Okay, and you can see very striking difference in terms of a color coding. And now this is the first detection of extreme UV photons at 600 angstrom from a galaxy. Okay, before that there has been no such thing. So that's why it's a very unique discovery. And now my students and the other postdocs, they are filling up this space here. So there are I think 10 plus more detections coming soon to fill up this space. So that would be very interesting. And why? Because what's the big thing about the 600 angstrom photons? You can see that if you look at the synthetic stellar spectrum or the intrinsic stellar spectrum, you see that at 912 there is a sharp drop, which is Lyman break. And then there are this spectrum rise with different slope. We don't have any observed data points here. If you produce more data points here, that would be much more helpful to constrain the ionizing spectrum of a galaxy. We have also a very interesting object detection at redshift 5.9. And we have a detection is 3.8. We are collaborating this with MUSE, which is at the moment the current state of the art, the integral field spectroscopy, and this is going to be very interesting because we are seeing signature of like a POP3 stellar population within the galaxy, which is a metal pole. Okay, very metal pole. So this is upcoming from this AstroSat deep field, UV deep field, AUDF. In future, what we are trying to do now, that I showed you like not only 2 observations which were done like in 2016, which is the guaranteed time observations. After that, there are many more observations has been done on this field and around that field, and these are the different pointings. Okay, and the intersection of this pointing is going to be the AstroSat ultra UV deep field. Okay, and it's going to be the one of the deepest UV deep field probably in the next several years, I think, because there is no FUV telescope. Okay, if I'm not mistaken. Yes, so I mean there is one in HST, but we know that they are not doing this, and also they have more time they invest. The noise is also rising, so they cannot actually go deeper, so that there is a limitation there. So with far ultraviolet telescope on board AstroSat, we can actually do this much better, and this is going to be a very value addition to the community. Okay, so the team is like is increasing with more and more people, students and postdocs here, and including external collaboration. So this is really a good thing that is happening. I just wanted to mention that this AstroSat UV deep field is a very unique facility that is with us. You know, most of the time we take data from elsewhere. Now it's our thing. That's the big thing. It's feel good. Anyway, so thank you for your attention, and I'll take questions if there are any.
Yes, sir. How do we know after the dark age that the stars which were getting formed were massive?
How do you know that after the dark age?
After the dark age, you stated that the stars which are formed at the time after the dark age were massive stars. How did we come to that conclusion?
Yeah, so the when the stars from like, if the metal helps you cooling. Okay, because the stars form from the gravitational collapse, right? So you have a hydrogen gas, will collapse and collapse, like no, there is like this from the so if you how do you say? So if you do not have metals, then one element is like going out, is like the cooling. Okay, so in absence of cooling, there will be like the kinetic temperature will hold the collapse, and that's how it's like most massive structures form.
Okay, and then also about the reionization you had stated.
Yeah.
You also stated that the reionization is still a mystery. But wouldn't that be because massive stars radiate at higher frequencies as well? So maybe gamma rays would have helped in reionization.
Possible, because I don't know if it will go into the gamma ray phase. The main issue is that, like, if you see the gamma ray, the sources that emit gamma rays, you often like think it's like the black hole activity, but whether the POP3 stars had chances to make black hole, there could be, but I don't think I will be able to answer this, because I don't know whether it will. Because it's a very short clip, like only 1 to mega year. If you put the numbers, the lifetime, it's like really short. So they will go into the explosion. And after that, there will be further collapse, but then we are not like talking about the POP3 anymore. Do you see the point?
Yes, sir.
So I don't know actually this. And yeah,
Okay.
good question.
Thank you, sir.
Yeah. So I have two questions. One is that what is the next big challenge that AstroStat collaboration is venturing into?
Mm-hmm.
And second is that what will be the scientific outcome from those challenges?
So you mean to ask that the AstroSat collaboration, because that's the future collaboration?
Yeah. I mean, like, what is the challenge that you are actually venturing into?
Okay. From my study.
Yeah.
So we have the imaging. So what I mean is that whatever I have done using the AstroSat, because this is a UV imaging telescope, so I created images. So I can do photometry, but what I lack is the spectroscopy. So I don't have the spectroscopy from the objects, and without spectroscopy, I'm really stuck, because I need the redshift measurements. So for this, I depend on external. For example, HST has done, as I said, around 1,500 objects for which we know the spectroscopy in that field. Then there is Muse has done Muse deep field, which is also have the spectroscopy, which is around 1,500 objects. Okay, so I have always this. I'm stuck because of the spectroscopy. So without the spectroscopy, we cannot go ahead, because there are so many objects, but we do not know their redshift. So only few thousand objects that we know. That I think is a challenging thing for us. We could go into the photometric redshift using the photometric bands, but in this business, when we talk about detection of this Lyman conifer, one is very, very strict about the redshift measurements properly. So always they like to have things from the spectroscopy. So that is a challenging, and that is the challenging task.
Okay.
Hi. I cannot hear you because you probably muted.
Yeah, sorry. I was muted. Sorry. Very nice talk, and very informative. I was just also a bit curious about. I'm obviously not an astronomer or a practitioner of the field, but I was just very curious about the recently also the launch the James Webb Telescope. Okay. And
Yes.
so I hear a lot about that. It does the IR images in the IR and IR spectroscopy, and in that range. So I was just wondering that, can you how do these techniques? And you are also doing in the deep UV X-ray. AstroSat is absolutely capable of looking at X-ray, soft X-ray wavelengths to deep UV. How do these things complement each other? And how do you actually juxtapose the data observed at these very different wavelengths?
Yes, I think it's a very good question, and it's a very relevant thing to ask right now. As you have rightly said, the JWST does imaging and spectroscopy in the infrared side. Okay, now which will allow this. Remember, I talked about the very high redshift galaxy, redshift 10, redshift 11, and these for these objects we will know now the spectroscopy part. First of all, okay, so we will know their redshift measurement. Okay, and that will lead to like a lot of discovery. Coming back to like the infrared side, sorry, UV side, which I have, this will be giving you a completely different wavelength coverage, which will be complementary to the JWST. Okay, and that is why I just recently, like, it's like about a month ago, we were just talking about to few JWST scientists now. So we are setting up a collaboration, because what I have is in the UV, I can also like go almost like a redshift 4, 5, which is also like very good. And then I sample a redshift, the wavelength range, which is really short. Okay, like 400 angstrom or something like that, which JWST can't. So this will be a good synergy actually. Okay, not only this, I think this will be also not only JWST, the few other the big facility that is coming up. This UV deep field will be like really useful in that sense, because our unique capability of probing the extreme UV part. Yeah.
Thank you so much. Yeah.
Thank you.
Yeah, I'd also like to thank the speaker, Ravi. It was really very wonderful. Okay. So thank you, Dr. Saha, for joining us on this wonderful experience. Thank you.
Thank you very much. Thank you, everyone. Okay, thank you very much.
Ravi, there is one more sponsor like Incar. They are actually already sent the email, but it was on Monday. Vinayak, it is there. You talk to Vinayak, he has it, okay? Yeah. There is one Tektronix also is there. Something is there, Tektronix. Convergent technologies. Oh, okay. Okay, that's good. Thank you very much.